This video covers Young's double-slit experiment. Thomas Young first demonstrated interference in light waves from two sources in 1801. Now, interference effects in light waves aren't easy to observe because of the short wavelength involved. That means in order for us to see observable interference effects, we need to have two conditions. One, we need to have coherent light, meaning that waves must maintain a constant phase relationship. Regular light coming from, let's say, a flashlight or sunlight is not coherent, meaning that it's coming in at different phases. And we'll talk about phase again in just a second. And it needs to be monochromatic, meaning that the waves must have the same wavelength and therefore the same frequency in order for us to see these interference effects. Now, the way these two conditions were achieved in the olden days is by using two separate screens. The first screen had one slit in it, and it was used to create a single wavefront that illuminated both slits coherently. The second screen had two slits, and that meant that the light hitting one slit was the same as the light hitting the other slit, meaning that the waves were in phase and had the same wavelength and frequency. Now, Young's double-slit experiment had all of this, and the light from the two slits produced a visible pattern on a screen consisting of a series of bright and dark parallel bands that we're going to call fringes. Now, these bright bands are referring to constructive interference, and the dark fringes, or the dark bands, are referring to destructive interference. Now, the way we achieve these constructive and destructive interference are by these three different types. The first one is when the paths are equal, meaning the light travels the same distance from both slits and they hit the same area. Then they go through constructive interference. The second one is when the wave paths differ by a wavelength. So imagine a wave, and the path that they travel is exactly one wavelength different. You can see that they're still going to be in phase, so they're still going to have constructive interference. The other situation is when the path lengths differ by half of a wavelength. What that means is if I have one wave like this, and my second wave is exactly 1/2 wavelength off, you're going to see that I'm going to have destructive interference, meaning that a crest is meeting up with a trough. Again, crest with a trough, trough with a crest. So we're going to actually have the dark bands happen at these points. So now we're going to talk about the geometric construction of Young's experiment. So we need to define some variables, where d is the distance between the two slits, labeled here. L is the distance from the slits to the screen, down here. And then y is going to represent the position of the bands. So the y can actually be a positive or negative number because we're going to designate the center between these two slits as position equal to 0. So before we can move on, we need to make a couple of assumptions. Here we're going to assume that our length L is much, much greater than D, the distance between these two slits, so that R1, which is the path that the first light ray travels, and R2, which is the path that the second light ray travels, are approximately parallel. If that's true, then you're going to see a situation like this one. If these two lines are parallel, then the distance that R2 travels more than R1 can be represented by d sine theta, where d is the distance between these slits and d sine theta is this bottom portion here. So we said that we are going to have constructive interference when they are either lined up exactly, meaning there's no difference in wavelength, or when they're exactly one wavelength apart, or whole number wavelengths apart. So this distance, d sine theta, which is this bottom portion, if that is equal to m times lambda, then we're going to have constructive interference, where m is going to be referred to as the order number. So when you shine light through these two slits, you're going to see these bands. And these bands are representing constructive interference. If we say that this is y is equal to 0, this is m is equal to 0. We have no difference in wavelength. So we have no d sine theta yet. But over here, we're going to have m is equal to 1, 2, 3, as we move away. And then we can say -1, -2, but I like to just call them 1, 2, 3. So if that distance is half of a wavelength off, or any multiple half wavelength off, then we're going to have destructive interference. So you can say that this is 0. Here in the middle, where I'm going to have a dark band, is 1/2 m. And then we have 1, and then 3/2 m, and then m 5/2. And then again, we can say that we have negative values over here. Now for these problems, we also like to apply what's called a small angle approximation. What that means is, let's say that this piece is L. This is theta, and this is y. So when theta becomes very, very small, and we're saying theta has to be less than about 4 degrees, then the hypotenuse becomes very, very close to equal to L. So when that happens, then y becomes approximately equal to L sine of theta. Again, this only happens for small angles. And for the most part, that's going to happen when L is much, much greater than y, the distance in between, or the position between these two bands. So we can try an example here. It says a screen is 1.5 meters from a set of double slits, so that L is equal to 1.5 meters. The distance between the two slits is 0.07 millimeters, so that's D. And I can go ahead and start writing this in terms of meters, so that becomes 0.07 times 10 to the negative 3 meters. And we have a monochromatic light, or a laser, that shines on the slits, and the bright fringes on the screen are 1.2 centimeters apart. So we're going to label that as y. And we're first asked to solve for the wavelength. So we can use our first equation that said that d sine theta is equal to m lambda. So this picture I drew down here is the situation that we're looking at. So I want to solve for lambda. That means d sine of theta over m is equal to lambda. Now here we're going to make the substitution that we have a very, very small angle. Again, that's true for most of these problems. So if that's true, then L sine theta is equal to y, and sine theta is equal to y over L. So I can go back and replace sine theta with y over L. So if I plug in all of my numbers, I should get 5.6 times 10 to the negative 7. That makes sense because wavelengths are about 560 nanometers, or 560 times 10 to the negative 9 meters. So again, all of these three things are equivalent. So this is about yellow light, actually, right in the middle of our visible light spectrum. The second part asks us to solve for how far from the center of the screen is the first dark fringe. Well, now if we're focusing on dark fringes, we're going to look at when m is equal to 1/2. And this is for part B. So we can use the same equation and the same substitution, so that d sine theta is equal to m lambda. Now our wavelength is not going to change because it's not entering a new medium. It is simply being diffracted. So I'm going to substitute sine theta for y over L. And I want to get y by itself. So that gives me y is equal to m lambda over dl. So if I plug in all of my values, you should see that that is going to give me exactly half of 1/2 centimeters, which that makes sense because if from here to here is 1/2 centimeters, then the dark band happens here in the middle. Shouldn't make it the same color. Our dark band happens here in the middle, which is exactly half of where my light bands occur. So again, you should get exactly half. So in class, it's going to be helpful to have seen what this looks like. This bottom section here, it's a double slit experiment that we've been talking about. So again, the pattern that you see are these bands of bright and dark lights. Now in class, we're going to talk about the single slit pattern, which again is not something that's intuitive. If you were to shine a light on a single slit, you would still get the same diffraction pattern. It would actually just be a little bit wider, and we'll see the math of that in class.